Now we can move on to the next speaker, who is Michele delli Veneri, who will also from the University of Naples, who will present a classification system called the HyCastle. So I will again 12 minutes. So if you you're already there. So 12 minutes with a 1 minute warning, and your time will start now.
Okay. So hi everybody, my name is Michele Veneri from Naples. As said, I would like to talk to you about a novel hybrid classification system based on typicality, labels, and entropy, also known as HyCastle, that I developed in the first year of my PhD with my research group. Now, the first question is, what are hybrid models? Most of you probably are familiar with both supervised classification models and clustering models. Supervised classification models use labels and features to try to approximate a functional mapping between input and labels. On the other side, you have clustering models for which labels are not known that try to identify instances that share common properties, or in another way, find the interdependencies between data. Now, hybrid models are born from the intuition that we can combine clustering and supervised classification, or in another way, use the clustering results to improve the classification results. In particular, these type of models are usually constructed by combining a density or graph-based clustering algorithm with a supervised classification algorithm. In the last 5 to 10 years, they have been shown to have higher performances than when compared to classical supervised models, and they seems to be more robust to both class and attribute noise. On the other side, because they rely on clustering algorithms, they have to make some basic assumption on the data distribution or cluster shapes and numbers. Because they are presented as frameworks, they keep separate the classification and clustering parts, and they do not consider directly the impact of noise on their performance. For such reason, we developed HyCastle in order to keep most of the pros of this algorithm while avoiding the cons. Now, of course, the first thing that we needed was a way to map interdependencies in the data in a totally unsupervised way. And for such reason, we borrowed from Angelo et al. 2017 an indicator called typicality. Now, typicality is a point-like measure that can tell you how close to the mode of the distribution is an instance. And it's derived from the cumulative proximity, also known as centrality in graph theory. Now, if you take the graph on the bottom left of the screen, that's the PCA visualization of an artificial training set made with 50-dimensional multivariate Gaussian distributions divided in 3 classes, and you compute the typicality distribution of such dataset, and then you rank it, taking the point with the highest typicality, so the one that has more close neighbors, and then by ranking it with a metric, you get this distribution that you see here. It's easy to see that with distribution, you can define clustering point around to which you can map the other instances, and thus you can form a very fine clustering of the dataset. We use this clustering as the first step of our algorithm, because we believe that the optimal solution for a problem may lie between somewhere in the middle, where on the left you have this very fine clustering, completely data driven. On the other side, you have your labels and what you can learn from them. So we're seeing now the workflow of the HyCastle training. So we use the typicality to form the initial clusters. We compute the cluster barycenters, their distance distribution, and we define a topological threshold. The clusters are divided in n+1 groups where n is the number of classes in the data, plus 1 groups contain spurious clusters, so cluster containing more than 1 class inside their assigned instances. Each group of cluster we construct a graph over it, and we, of course, the cluster will be the nodes of such a graph, and we create an edge between pure between clusters if their mutual distance is lower than the topological threshold. While for spurious clusters, we are also need to calculate the Gini index of the two clusters, and we will aggregate them if their union will minimize the Gini index of the total cluster configuration. So you can think of it as an entropy minimization algorithm. We then will, in parallel, aggregate all these clusters, and then for each cluster, we ask a classification and regression tree, and this is the supervised part of our algorithm, to return the leaf index that predicted each instance of the cluster. You have to understand that the classification tree now is asked to solve a much easier problem that would be classifying the total data set, because it's extremely localized in the parameter space. Anyway, if more than one leaf is returned, then it means that the data set could be divided, the cluster could be divided, and we divide them, and then the aggregation and separation cycle runs again until you have a final cluster configuration. Then prediction is totally distance based. We take the k representative for each cluster, compute the distance from an unknown instance, transform this distance distribution in a probability distribution, and then transform the probability of an instance to be assigned to a given cluster to the class probability. Of course, because this algorithm does probabilistic prediction, you can insert as much as external information if you want here as a prior to this probabilistic distribution. Now, to test the HyCastle performances, we took more than 35 benchmark datasets and compare it with both hybrid state-of-the-art models, in particular the two HCFC from Xiao and the graph-based model ABDG from Bertini et al. 2017, and a plethora of classical models, C45, support vector machine, naive Bayes, MLP, all the models that we could. To make us a fair confrontation as we could, we employed a 10 times tenfold cross-validation strategy, optimize the parameter for each of these models through a grid search, and utilize ordinal encoding and one-hot encoding for all models that cannot handle categorical features. You can see here there are two box plots relative to the two experiments of 23 datasets and 16 datasets. You can see HyCastle is always on the left. We report a higher average accuracy over the 23 and 16 dataset with a lower scatter. And to back up our hypothesis that HyCastle is the best model, we run a Friedman, Ivan Davenport, and Ayemi post-hoc test with a null hypothesis that all models shared the same performances, and the three tests were rejected. It was very important to us to test the robustness of our model to noise, because it's in astrophysical experiments is often extremely present. And so we injected a higher and higher level of noise, of class noise in the data. And as you can see, this is over the 23 dataset HyCastle compared with the best models. You can see that HyCastle always keeps a higher accuracy, thus demonstrating that it is more resilient to noise. And we believe this spans from the fact that HyCastle is in a way not relying totally on the labels as other classification models, but is using way more the inherent data topology. Now, we wanted to make an astrophysical use case of interest to both us and you guys. For this, we took the strong gravitational lens finding challenge. The challenge results were presented in the paper from Metcalfe in 2019. Basically, the challenge simulates 100 by 100 single channel images, both containing lens or non-lens events. Of course, the classification goal is to divide lens events from non-lens events. The model performance were evaluated to the area under the receiving operating curve score, or AUROC. And the two best models were two deep learning models, LASTRO EPFPL based on a CNN, and CPU DepLens ResNet based on a recurrent neural network ResNet. The models reported an ROC respectively of 0.93 and 0.92 on the task. HyCastle cannot work directly on images, so we had to extract features from those images, and the features were extracted through a ResNet 50. Why a ResNet? Because we wanted to, of course, reduce the data dimensionality while preserving the high frequency ones. As preprocessing, as the models the winning models that I cited, we did some standard preprocessing steps, so rotation, vertical flips, bad pixel maxing, resizing, standardization, etc. And as fully connected layers at the end of the ResNet that in a way is only extracting the features, we have the last flattened layers with the 2048 neurons, then a ReLU, and a hidden layer, and then a softmax that's outputting the class probability of being a lens or a no-lens. We train the ResNet, and then we use the ResNet trained features, in particular on the flattened layer, as input for HyCastle. And of course, HyCastle too has a probabilistic prediction. Here you can see the results of both the ResNet and, yes, thank you. You can see the results of ResNet and HyCastle and the other models. You see, as expected, the ResNet keeps the AUROC of the other models but due to similarities. So we get around at 0.92, while HyCastle has a quite a huge improvement over the other models with an AUROC of 0.95. HyCastle is completely developed in Python and is using the sklearn framework. So whatever metric you want to use, whatever modification, you just have to treat it as a standard sklearn model. The GitHub page of the model is not quite ready yet. We are waiting for the model to be published by the paper where we have submitted the paper, and that's all from me. Thank you for your kind attention, and if there are any questions, please feel free to answer them. Feel free to ask them.
Oh, thank you so much. Spot on time. Any questions to put to Michele? Anyone at all in the chat? There's no one. Well, can I ask you about this issue of labels?
I have a question. I can raise hand. Sorry.
Okay, go ahead, please. Go ahead.
Oh, thank you for great talk. You use real lens images or model ones? I don't get it. Sorry.
The challenge is based on simulated images, but the challenge was hard by itself. So I don't know. I've never tried to use it on real images, but we will try soon.
It will be interesting. Yes, it will be interesting. Thank you again.
You're welcome. Thank you for the question.
Any more questions? If I may, you mentioned, so your last slide 42 rings a bell. I was curious when you mentioned that your HyCastle algorithm is less dependent on the labels and therefore is more performant. But does that mean that somewhere that you are more sensitive to the dimensionality of the problem, so the number of input data? Could you clarify that?
Yeah, that's the beauty of it, because typicality is completely unshaken by the dimensionality of the problem. We get a first clustering configuration that extract as much information from the data without worrying about the dimensionality. Then we would be prone to, we will suffer from high dimensionality if the cart that we are training would span the entire dataset. But because by then we have already localized the cluster in very fine region of the parameter space, then we don't care anymore.
Okay, thank you very much. That's very nice.
You.
Anyone else with a quick question, perhaps? Raise your hand. Oh, Well, I'm sure in the chats at later times there will be occasions to feed questions to Michele. So thank you very much for your talk. And now we come to the thank you very much. We come